Okay, so let's continue. Before we start, I will assign you homework number 1, which is the homework problem at end of chapter 1 of our textbook. So most of the time, I assign homework based on our textbooks. If we finish part of the chapter, so I will assign some homework from our book. And so I skipped chapter 1 totally because I already mentioned that this is not a review of your modern physics. So chapter 1 belongs to the subject of the modern physics in electrophysics department course. As a result, I skip all the content in chapter 1, but we will come back and forth from time to time. So you should know about black body radiation, you should know the photoelectric effect, you should know Compton scattering, you should know Stern-Glock experiment for spin, and you should know electron diffraction, and you should know Bohr's theory for hydrogen atoms. You should know everything about chapter 1. Okay? Since you are here, you should know everything about chapter 1. And if you have not studied thoroughly the chapter 1, and you are able to understand all the contents in chapter 1. So without telling you the details of chapter 1, this is your review of your modern physics, meaning you do the homework exercise for chapter 1 for your own sake, for a review of the important concepts in modern physics, namely the quantum physics. So there will be some homework about the black body radiation, photoelectric effect, Compton scattering, and Bohr's theory, and so on and so forth. So you take this opportunity to challenge yourself and to really get familiarized with the birth of the quantum mechanics or quantum physics at the end of the 19th century and the beginning of the 20th century. Okay, so, and we start from chapter 2, which is what I'm doing now to give you a review and some fundamental basic principles of quantum mechanics that you may not be familiar with. So if you have questions and concerns, please let me know. Good. So let's start the introduction to the basic principles of quantum mechanics. As I mentioned last time, so the particle-wave duality has everything to do with this Heisenberg uncertainty relation and the fundamental limitations of what we can and cannot know in quantum mechanics. So, and this boils down to the very important statement I wrote here, which is the connection between the measurement, experimental measurable quantities, and the particle-wave duality. As I mentioned, you can only see one phase at a time. You cannot see the double phases of a quantum particle at the same time. But which phase is more fundamental than the other? Well, the answer is the particle nature is the more fundamental nature that you could observe experimentally, which means that the particle-like properties of quantum matter are observed directly from experiments. It's experimentally directly observed in experiments. However, the wave-like properties can also be observed experimentally, but microscopically, if you look at this in more details, up to, say, single photon, single electron level, at that single particle level, you only see a particle nature of a quantum matter. But if you perform experiments many times, or you look at the collection of many particles, many quantum particles, and you see some wave-like properties emerges out of a many particle or many experiments, and therefore these wave-like properties of quantum particles are only inferred. It's a secondary nature of a quantum matter. The first nature is the particle nature. The wave nature is the statistical averaged or inferred phenomena. But even though this is an inferred properties, you can only observe directly from the experiments. But what you should know here is that this wave-like properties are a collection or statistical sense that you could observe experimentally. As an individual particle, only the particle properties should show up. But if you design your experiments in such a way that you can only probe the wave-like properties, not the particle-like properties, then you don't see the particle nature of your system. You only see the wave-like nature of the system. We will give you an example in just a moment, but this is a very important point that all the quantum particles are particles. Okay, if you look at this at the atomic level, electrons, photons, whatever quantum particles, you name it, they are all particles. But sometimes the particle nature of those quantum particles are not showing up because you design the experiments which does not allow this possibility to show up. So let's look at this example, particularly very important link between the particle wave duality and Heisenberg uncertainty relation. So this is very important point. Unfortunately, you cannot find much descriptions in the textbooks that link these two very important concepts. Okay, so now we will really strongly link these two concepts together. So as I mentioned, you can only see one side of the face at a time, and either particle or wave nature that can be probed from your experiments, and you cannot see both faces of the quantum matter at the same time. But if you really want to see the double faces at the same time, then you violate Heisenberg uncertainty relation. Okay, so the Heisenberg uncertainty principle forbids you to know the double characters of quantum matter. And this is a fundamental limitation of what we can and cannot know about quantum particles. Okay, so and these two very important concepts go side by side in quantum mechanics. But oftentimes in those textbooks, the authors did not emphasize this link between the Heisenberg uncertainty relation and the particle wave duality too much. Okay? But in order to really claim that you understand quantum mechanics, you really have to understand this connection. So what is this Heisenberg uncertainty relation telling us? This, as I mentioned many times, and this product to arrow bars, delta x and delta p, is always greater than or equal to h power over 2. This sounds really simple, but we will derive this from quantum mechanics following this Dirac's notation. So that's for later, but we will derive this. But here, we just take this for granted, right? So suppose we have such uncertainty relations, and then how do we understand this particle wave duality? Great. So let's just look at this famous example, this double-slit example. Suppose that this is electron diffraction, or electrons passing through this double slits, and leads to those beautiful interference pattern. And as I mentioned last time, that we know this interference pattern only after we wait, we accumulate many electrons hitting the target, hit on the screen, and those random electrons hit on the screen, when you collect all this data after a certain amount of time, and you can see this wave-like behavior. This is precisely what I meant just from this statement, that if you could take a snapshot, you could see these electrons hitting on the screen randomly at the first, and then this pattern starts to emerge only after a certain amount of time. And this is precisely what I meant, that this wave-like properties is the properties that inferred, or statistically, this in the statistical sense that you see this wave-like properties. So the wave-like properties of quantum mechanics really depends on measurements and how you design your experiments. So it really depends on how you probe, how you observe, what you want to see, what kind of experimental design that in your mind that you can realize wave-like properties, such as this. So you design a fixed screen on the other side of the double slit, and then you wait until this electrons passing through these two slits, and you wait until some time, and you collect all these images on the screen. Okay, so there's really a pin which fixes the screen. So let us just ask this question. So if I'm a stubborn person, I don't believe this particle wave duality, and I insist, well, I should see the particle properties of this double-slit experiment from electron, and because electrons are still particles, right? So why can I see the particle nature of electrons in these experiments? And therefore, I ask this question to myself, can I know the particle nature of this experiments of this electron? Meaning, the particle nature refers to the fact that I know the position and I know the momentum, especially the momentum of the electrons, right? So the exact momentum and position, and also which implies that which electron comes from where. Okay, so this is a really difficult challenge. So I know those random hits on the screen, but do I know which electrons come from where? For example, if I like to know, say, this electron hitting on this spot, so where does it come from? Slit number 1 or slit number 2? Do I have the ability to know this? Can I really know this? If I really know this, then I see both particle and wave properties of these experiments. But of course, the answer is no, you cannot know. Why cannot know this? Well, because you violate the Heisenberg uncertainty relations if you really insist this to be measured. So we don't know why the Heisenberg uncertainty principle is this principle, and we do not know the source of the Heisenberg principle, but what we do know is that we cannot violate Heisenberg uncertainty relation because this is the most fundamental principle in quantum mechanics. Of course, this is assumption, but this assumption could be proved later, more rigorously, more mathematically, but we should rely on this uncertainty relation at this point. So here comes the dilemma. So if you really want to know which particle comes from where, then we will see in just a moment that this effort will destroy this Heisenberg uncertainty relation, meaning we will violate this relation. Because we cannot violate Heisenberg uncertainty relation, and therefore we cannot at the same time know this wave-like properties of this experiment and also the particle nature of this electron. Okay, so this experiment is specially designed to see the wave-like properties because we fix the screen and we allow the electron to pass the hit on the screen, and therefore we know the wave nature. But if you don't fix the screen and we allow this screen to move along the vertical axis, and as a result we could know the momentum of the electrons, which may come from the slit 1 or slit 2, because this will lead to different momentum when this particle hit on the screen, right? Okay, so once we move this vertical screen and we destroy this interference pattern at the same time. So we will prove that it is not possible to do so. So let me just illustrate this point by some simple calculations. Okay, so the separation is D, and let's say this is the momentum of the electron passing through slit 1, and the other one is the momentum vector that electrons passes from slit 2, and both passes, this electron will hit on the screen the same spot like this. And the distance between the screen and the slits is capital D, and this capital D is really, really large compared to this separation between these two slits, little d here. So in order to identify which particle comes from where, I should remove the pin, as I mentioned, to allow the screen to be moved vertically. Okay, so if the screen could actually move up and down, and I can really see this momentum change when this, say, the particle from slit 1 hit the screen, the screen should actually receive some momentum impulse that will actually move the screen, either upwards or downwards. So, and you could put a sensor here. So this sensor detects the momentum of the particle that hit the screen, where the screen is actually movable along the vertical direction. So you will very clearly see there is a y component or vertical component of the momentum of your incoming electrons carrying this minus momentum with this electrons coming from slit 1 hits the screen, and the vertical movable screen will tell you that this particle, when it hits the screen, carry that much momentum, and this factor comes from the small angle between this horizontal axis and the trajectory of the slit 1 particle. And assuming that this capital D is much larger than D, small d, separation between these two slits, and this is simply just 1/2 of sine theta, where sine theta is just simply just d over small d. So that's really simple. And likewise, if the slit 2 electrons hit the screen on the same spot, and what this movable detector will tell you is that this particle will carry this amount upward, and the first one is actually downward. Right? Okay. So let's just examine this, if this happens, and what is the consequence of such a detector, and what is the uncertainty to find this momentum of these particles coming from slit 1 or 2, and your uncertainty to really know where the particle is along the y direction. So as I mentioned, it's py, so it's up slit particle carry minus pd over 2d, and py for down slip particle carry pd over 2 capital D amount of momentum. So in order to identify which slit that electron comes from, you need to have a better resolution in momentum detector, right? In order to really resolve this difference in magnitude of this py component electron hitting on the screen. So as a result, we can identify the slit from which the electron comes from only if the momentum of this recoiling screen is measured with an accuracy of this difference between these two momentum. Right? So you need to have a very good resolution detector, right? And the resolution has to be at least that much. Delta P goes to PD small d over capital D. So I could tell the difference between these two momentum for these two electrons hitting on the screen. If I can tell from my detector, then I can identify which electron comes from where. You get the logic. I got a better resolution detector better than this, right? So to get a resolution better than this, delta P must be less than this number, right? The arrow bar in determining this momentum of these two particles should be less than this value. Otherwise, I cannot resolve this distance, this difference. Okay? So the arrow bar should be small enough. Okay, smaller than that value, and that value is difference between these two momentum. Right? I need to know the difference between these two momentum, at least. And that tells us that this delta P, the arrow bar, to identify this momentum of the particle should be less than this amount. So, however, you immediately know that if this is going to happen, and you could apply this Heisenberg uncertainty relation, so delta P times delta Y has to be larger than or equal to h power over 2. As a result, from the Heisenberg principle, we know that delta Y has to be greater than or equal to h over delta P. So, which means that delta P times delta Y greater than or equal to h. Of course, there's a factor of 2 pi, but I don't care about this 2 pi. So 1/2 of h bar is actually h over 4 pi. Okay, But this 4 pi is within order of magnitude, so let's just forget about this difference and just make very crude approximation. So at the very core level, very crude approximate level, this delta y has to be greater than or equal to h over delta p, which is this value, lambda d over d. And remember, from deployed matter wave, this momentum of this quantum particle p is actually h over lambda. And lambda is the deployed matter wave. Okay, so from Heisenberg uncertainty relation, we know immediately that error bar to determine the position of this electrons hidden on the screen should be greater than lambda capital D divided by small d. Okay, but what is this value, lambda capital D divided by smaller d? Well, this is nothing but the separation between two maximums. This value is precisely the difference in the interference pattern that you will see between central maximum and the first local maximum. If you go back to general physics, the interference of the double slit, you will immediately find this number from your textbook. Distance between the central maximum and the first maximum of your double slit interference pattern goes like lambda times capital D divided by small d. Good. And this is a disaster, because in order to really exactly know the momentum of your electrons and know which electron comes from where, you have to sacrifice the accuracy in determining the position of that electron. And if this screen is allowed to move vertically, and this will lead to this uncertainty or error bar in determining position of these electrons on the screen, and this error bar delta y precisely is greater than that distance, which means that you cannot tell anything in between these two maximums. It's totally a blur. You destroy your interference because you cannot resolve this distance. You don't know whether this is the maximum, the minimum, or a local minimum, or global maximum. You have no way, because this is out of your error bar. Your error bar in determining the y direction is greater than that distance, which means that you cannot tell anything. You cannot tell whether there is interference happening on screen, because you have no resolution to resolve that distance. Do you see this argument? Do you understand this argument and the logic? Okay, so this is the magic of quantum mechanics. Even though you know precisely that each quantum particle carries momentum with its particle nature, and also as a collection of many quantum particles, you see these wave-like behaviors as a statistical average, but you cannot know both at the same time, because if you want to know both, for example, if you want to know the particle nature in its wave-like experiments, then you violate the Heisenberg uncertainty relation, which you cannot. Okay? And this kind of thought experiment or very rough estimation tells us that if you really probe the wave-like properties from the experiments, and you need to really make a special design of your experiments so that you should fix the screen. You should not let the screen to move. If you really want to know the particle momentum and allow this screen to move, and you don't see the wave properties anymore. The wave property is gone, okay? Because you totally smear out this interference pattern, because you have no good enough resolution to see this interference pattern anymore. Okay, and therefore, if you really want to see this experiment from this specially designed equipment, and you only see this wave-like properties from this experiment. Of course, you could design another experiments to see the particle nature of the quantum matter, and if you do so, then the wave property is gone. By the same reason, Okay, if you want to know both, then you violate the Heisenberg uncertainty relation, and which is a more fundamental limitations in quantum mechanics. And this is what I emphasize many, many times. And you should really remember this fundamental limitations of quantum mechanics and which experiments shows which part of the nature of the dual double phases of the quantum matter. And we will come back to this type of argument many, many times in the future. But this is the simplest possible thought experiment that you could imagine, and to link between this particle wave duality and Heisenberg uncertainty relation. Okay, so later we will ask very, very similar questions from different problems. For example, this potential barrier problem, whether we could really probe the electron tunneling through this potential barrier in quantum mechanics. We know that electron can actually tunnel through the barrier that is higher than this original total energy, which is classically forbidden. Okay? But quantum mechanically, electrons can tunnel through the barrier. Okay? But how come? We cannot have a very good intuition on this phenomenon. This phenomenon is real because this is the basis of the equipment called STM, standing tunneling microscope, 扫描式电子显微镜. Okay, so this STM technique is a very powerful technique in all these modern devices. And this phenomenon is real, but this understanding why this electron can actually tunnel through the wall, and how do I see whether there's really a particle inside the barrier? This is, again, the same type of argument. So we have to assume that particle does pass through this barrier, but there's no way that we can confirm this experimentally. It's just experimentally, quantum mechanics, especially the Heisenberg principle, forbids us to really detect whether there is really electrons ever pass through this barrier. So if we really want to know electrons ever being inside this barrier, then we have a problem. The electrons never tunnel through the barrier. So if you are very stubborn, want to see the other side of the nature, then you lose your original motivation to observe this phenomena from the beginning. So such a dilemma happens many, many times in quantum mechanics, so you should enjoy this type of argument in the following course. Good. Any questions so far? Yes?
What's number recurring?
什么？
那个是 recurring.
哪一个？
Only 是 only time.
Only if. That's right. This is a requirement.
对，我说底下那个。
Only if the momentum of the recoiling screen. Recoiling means, you know that, right? Okay. Good. Okay, so let me tell you that this kind of argument will show up in your midterm, hopefully final exam. So you should be very, very familiar with this argument. Okay, so this logic and argument and understanding is much more important than the calculation itself. This is the essence of quantum mechanics. If you don't understand this, you don't understand quantum mechanics. Okay, and this is something that oftentimes you will not hear professors giving lectures in quantum mechanics, and also it's really not often that you see in the textbooks. This is my special note and for you. So then I will move on to introduce this Schrödinger's wave functions and the probability interpretations and derive the Schrödinger equation. So this is somewhat a review of your modern physics. Okay, so for those of you who already learned this from your previous course, please be patient and you will learn something that you didn't know. One more thing. So in my notes, we could measure this probability distribution of a quantum particle by measuring the square magnitude of their wave functions, square of psi of x, but we cannot measure the wave function itself. The wave function is not experimentally measurable quantity. We cannot measure Schrödinger's wave function, but we can measure the square magnitude of Schrödinger's wave function, which has a probability interpretation as we mentioned last time. But the Schrödinger's wave function plays a similar role as electric field in classical mechanics when you study this interference from this double slit or single slit. So it is the vector-like object and satisfies the linear algebra, and we could make a linear combinations of the two wave functions, and we can measure interference of a single quantum particle. Okay, so then we could more mathematically write down this wave function for a free particle. So they're usually described by a plane wave. So for a plane single particle, you could use a classical plane wave to describe such a free single particle in quantum mechanics. And we know very well that plane wave is described by this complex wave functions. However, we know that this are quantum particles. As a result, it satisfies the de Broglie relations and also very simple relation for light or electromagnetic wave, such as this omega is the angular frequency of this quantum particle, is going to be the wave number k, which is defined as 2 pi over lambda, and lambda is wavelength, times c. C is the velocity of that single particle. But oftentimes, the quantum matter is consisted of many, many free particles or interacting particles. So you can imagine that if you want to describe the realistic object in quantum mechanics, the single particle plane waves is not enough. It's not sufficient to simply just use this plane wave to describe any particles, but instead, any object with a finite width could be considered as a wave packet, which means that this is a group of, say, electrons and ions and whatever this materials inside your system, and each elementary particle could be considered as some kind of a plane wave, and you have many plane wave to be superimposed. So you superimpose those plane wave with different amplitudes A and B as function of this wave number, and you could compose this wave packet and express this in terms of such a integral over all possible single particle plane wave. Okay, so imagine I could combine all these different single particles with different amplitude A and B, right? So I forget about B and just look at this A coefficient, and A depends on this wave number k. For different wave number or momentum, this momentum is h bar k in quantum mechanics. Remember that, de Broglie relation. So at different momentum, you get different amplitudes. So you could superimpose all such a different amplitude wave, plane wave, and to form a wave packet. So next time, we will start from this wave packet, and we should, again, derive this Heisenberg, or check the Heisenberg uncertainty relation, and then we could derive the Schrödinger equations based on this wave packet description of quantum matter. Okay, so enjoy reading chapter 1 and start to read chapter 2. And if you already learned this, simply just read this textbook on chapter 2 as your storybook. Great. I will see you on Wednesday, and enjoy your homework.